Welcome to Klein's Calculus. I did this yesterday, but without the microphone. The audio was way off. We're going to try it again today with the microphone and see if it works out better. However, the notes are already done, so I'll just be pointing as I go. We're going to look at derivatives of trigonometric functions today. And from your exploration on page 141, we learned that the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative sine of x. And this notation means the derivative of the sine of x with respect to x is cosine of x. The derivative of the cosine of x with respect to x equals the negative sine of x. From these two things, we can find the derivatives for all the other trig functions because they can all be written in terms of the sine and the cosine. We can also mix and match. We can compose, look at compositions of trig functions, and use our product, power, and quotient rule to find those derivatives. So that said, we're going to look first at finding the derivative of y equals x squared times the sine of x. And we look at that as a composition of u, x squared, times b, sine of x. So the first thing you probably would want to do is write out your power rule, or product rule, because you've got this product of two functions. And then and that's just going to be the first times the derivative of the second, plus the second times the derivative of the first. And doing this, the first is x squared, and then you're going to multiply it by the derivative of the sine of x, cosine of x, plus, now you write down the second, and then you'll write times the derivative of x squared, so you've got 2x. When you do that, to put it in more conventional form, we usually put whatever this is in front of your trig function. So you're going to have x squared, cosine of x, plus 2x times the sine of x, and that's your y prime. Now, if you had a function such as this one, where you've got a difference or a quotient here, u equals the cosine of x over 1 minus sine of x, you would have u divided by b, and you'd know you'd be using the quotient rule. So I'm going to take and write out my quotient rule here. U prime is going to be low times the derivative of the high minus high times the derivative of the low over the square of what's below. Make sure that you start with this bottom function first, or you end up with the wrong sign. Okay? I saw a little bit of that happening the other day. When you do that, you write down your low. Your derivative of the cosine of x is the negative sine of x, minus, and you've got the top now, cosine of x, times the derivative of the bottom, which is the derivative of 1 is 0, minus, and the derivative of the sine is the cosine of x. So you have cosine of x times 0 minus cosine of x. And all of that is over 1 minus sine of x squared. Now to simplify this further, we're going to take and distribute our negative sine of x. So I've got negative sine of x plus sine squared of x, because the negative times negative made a positive, minus, and here this gives me cosine times cosine, cosine squared, and a negative times the negative here. So minus the negative cosine squared, which is a positive cosine squared, all over 1 minus the sine of x quantity squared. Now the thing to remember here is we have an identity. Anytime you've got the sine squared of x plus the cosine squared of x, that equals 1. So I'm going to take, and in my final answer, I'm going to make this 1 minus the sine of x. You could say negative sine of x plus 1. I just like to not have those negatives out front. Sometimes we lose them. Over the quantity, 1 minus sine of x quantity squared. So there's your final derivative. And this is an important concept to keep in mind, is anytime you've got that sine squared of x plus cosine squared of x, you may just substitute that for a 1 and get a nice, easier to read answer. Now let's look at our sine and cosine functions, and let's use that product and quotient rule to find the other trig functions. Actually, let's use the quotient rule. If you look at the tangent function, we can take the derivative of the tangent by taking the derivative of the sine of x over the cosine of x. That would be u and v. And we know that's going to be low d high minus high d low all over the square of what's below. Well, below is cosine of x. The high, I need the derivative of that, so I've got a cosine of x again. Minus high, the sine of x, below, the derivative of cosine is negative sine of x, all over cosine squared of x. Well, this is going to give me cosine squared, minus the negative is going to be plus, and I've got cosine squared of x plus sine squared of x over cosine squared of x. As we just found out, we can call that 1 over, this can be a 1 over the cosine squared of x, and you know 1 over the cosine is the secant, so that's really just the secant squared of x, and there's our derivative for tangent. Just the derivative of the tangent of x is the secant squared of x. You can, I hope you're just going to remember that, memorize it. You can always derive it using the quotient rule if you forget it. What about the cotangent? We can do the same thing, except we have to look at the cosine of x over the sine of x. So now u is cosine and v is sine. So we end up with kind of the reverse of what we had up here. We have the sine squared of x, the negative sine squared of x, minus the cosine squared of x over the sine squared of x. Well, I know if I have sine squared of x plus cosine squared of x, it's 1. So I'm going to just factor out a 1 here. And then I end up with negative 1 over the sine squared of x. And we know that 1 over the sine of x is the cosecant. So the derivative of the cotangent of x is actually just the negative cosecant squared of x. Okay? Now when we look at the secant, well, that's 1 over the cosine. So u and v. And if we think low d high, well, the derivative of a constant is 0, so that's going to cancel out. Minus high, 1, to low, negative sine of x, all over the square of what's below. Those two negatives will make a positive, and we have the sine of x over cosine squared of x. I'm going to be a little clever here and write this as cosine of x times cosine of x, because then I have the tangent identity here and the secant identity here. So the derivative of the secant is the tangent of x times the secant of x. Okay? Again, another thing to memorize, and if you don't, you know you can derive them again. And then finally, we'll look at the cosecant, which is going to be 1 over the sine of x. And once again, low d high, but that constant derivative is 0, so that's going to cancel out. Minus high d low, and the derivative of the sine is the cosine, over the sine squared. That's what's below this time. So I've got negative cosine of x over the sine of x times the sine of x. And the cosine over the sine is my cotangent, and 1 over the sine is my cosecant. So the derivative of the cosecant of x is negative, don't forget that negative, cotangent of x, cosecant of x. So again, good to memorize these things. If you don't get them memorized, you can always derive them using this quotient rule. Next thing I wanted to talk to you about is jerk. Jerk is simply the derivative of acceleration. If a body's position at time t is s of t, you know that's what we call our position function. The body's jerk at time t is going to be the derivative of acceleration with respect to time, which is actually the third derivative of position. Okay? So here's how it looks. We start with our position function, s of t. We take the derivative. Now we have velocity, s prime of t. We take the derivative of velocity. That's s double prime of t, which is the derivative of velocity, which we know is acceleration. How fast is our rate of change changing? And then when we take s triple prime of t, the derivative of acceleration, which is the second which is derivative of acceleration, the second derivative of velocity, and the third derivative of position, that is our jerk. When you think about the motion of a spring, and we're going to talk about that in just a second, it's described by S of t equals 5 cosine of t, so you know that means that it's going up. It's 5 times cosine of t, so it'll be going between 5 and negative 5, and it goes down and up and down. Well, the derivative of that would be how fast it was moving, would be negative 5 times the sine of t. So it's going to be going, the change in the speed is going to be changing more like this. And acceleration, now you just take your negative 5, you take the derivative of the sine, you get the cosine. And then the jerk, well, you take the derivative of your acceleration, and you got negative 5, but the derivative of cosine is the negative sign, so it actually turns it into a positive 5. So you can see the signs change because the cosine, the derivative of cosine is negative sine. I'm sorry, our video forgot to look at that. Now looking at our spring, simple harmonic motion, you can think about that, the motion of a weight just bobbing up and down at the end of the spring, and the sine and cosine function are great functions to describe that motion. So if you look at example 2 in your book, we've got a weight hanging from a string, and it stretches 5 units beyond its rest position, and then when you release it at t equals 0, it bobs up and down, so it's going to go up to the 5, down to the negative 5, up to the 5, down to the negative 5. And S equals 5 cosine of t is a great descriptor for that. So what are its velocity and acceleration? All you have to do to find those is take the derivative of the sine, or of the position function, to get velocity. And you know derivative of cosine, negative sine, so you have a negative velocity. And then take the derivative of the velocity to get your acceleration. Well, the derivative of the sine is the cosine, so the sine doesn't change there. We could do jerk, but we don't have to. Well, when you describe its motion, the first thing you'd look at is where does the velocity equal 0? And it's going to be where the sine of t equals 0, so it's going to be k pi, where k is any integer. And what about the acceleration? That is 0. A of t is 0. When the cosine of t equals 0, so it's at pi over 2 times k, where k is an odd integer. Now, how could you describe this motion? Well, knowing that, you could say that the spring is moving up, and here's, sometimes looking at the graph helps. This is v of t, negative 5 times the sine of t. So you can see it's going, the sine function always goes through 0, 0. So it's coming up to 5 first, and then it goes through, it stopped here, and then it's down to negative 5, and it's stopped here, and it's up to 5. And this is our velocity. So it's saying that it's moving faster till you get to pi over 2, and then it slows down and it stops, so it's at the top of its spring, and then it goes down and it speeds up going down till you get to 3 pi over 2, and then it starts coming back up, or excuse me, it stays slowing down till it gets to the very bottom here, and now it's going to start going up again, and it comes up, gets faster and faster, starts slowing down, although it's still going up till it gets to here. So it's moving up and down, and it moves up when the velocity is 0 to pi, 2 pi to 3 pi, 4 pi to 5 pi, down with respective velocities. Acceleration, you kind of look at your acceleration graph, and you can see it's 0 when acceleration is 0, and it's starting up here because it's cosine, and it's highest when the acceleration is 5, and it's going to be lowest when the acceleration is negative 5, and you can see that going up and down with an acceleration of 0 also. So hopefully that will help explain some things and ask more stuff as needed in class.